Hello, I'm Devendra Kapadia. I'm the manager of Calculus and Algebra at Wolfram. And this morning I'll speak about what's new in Calculus and Algebra. That'll cover a wide range of topics, starting from asymptotics, special functions, math education, function properties, and all kinds of stuff. It should be good for anyone who is a student, professor, research worker, anyone. So do come along. It should be great. Thank you. Okay, hello everyone. So I'm Devendra Kapadia. I'm the manager of Calculus and Algebra at Wolfram. And in this talk, I'd like to speak about what's new in Calculus and Algebra, what's happened in the last 1 year. And this is a kind of overview presentation. I'll give some brief ideas, but then we have a session to ourselves, 3 talks today, another talk tomorrow. So I'll try and lead into those talks. So I welcome you to stay for all these talks. They should all be excellent. So what I'm giving over here is just a brief overview. So here is an outline of my talk. So I'm going to begin with asymptotic computation, which has been our main theme for the last couple of years. And we have 2 new functions, asymptotic and discrete asymptotic, which are kind of super functions. They can take any input, function, sequence, operators, integrals, sums, etc., and they'll do the right thing. So I'll speak about those asymptotic computation functions. And then about mathematical functions, which include special functions. We have these new Heun functions, which are a pretty major advance in our special functions support. And we've done good work on documentation side. I'll speak about that. Differential equations, something that keeps on occupying our time. We try our best to keep up, and we always seem to fall a bit short, so then you put a little more effort, so I'll talk about that. We have a very nice program for function properties, things like continuity, singularity, etc., which should help everyone from, I'd say, pre-college all the way up to research. It's very deep stuff. Math education, of course, is core to our team. I think we are the math education team in the company from the Mathematica side of things. For many people, calculus is Mathematica and vice versa. So I'll speak about math education. And one last thing for the last year or so, I've been working on a linear algebra MOOC, a massive open online course. That's ready from my side. It should ship soon, whatever that means. So I'll talk about that. So let me begin now with asymptotic computation. So if you have a function like sin x, and you want to see what it does look like near 0, let's say. Of course, you know sin x is approximately x near 0. So you have this nice new function called asymptotic, which will just give you that leading approximation. It'll just say x for you. And so you have a nice leading approximation, but what if you want more terms? Well, we have an option called series term goal, and you can ask for more terms. So this function, by default, will give you a leading approximation. If you want a better approximation, give it the option, it'll do it for you. Now, that's one world, the world of functions. But then we also have the world of sequences. So what happens there? Well, we need a new function because for a sequence, everything goes to infinity in integer steps. So you have a nice new function called discrete asymptotic. So if you say discrete asymptotic of n factorial, you just get back Stirling's formula. And of course, that's the starting point for asymptotics a long time ago. You get back the nice Stirling formula, but then what if you go to prime sequence? So what's the asymptotic of prime sequence? That's n log n. And it doesn't matter that the prime numbers always, they have slightly more than the n log n, but asymptotically, the sequence goes to 1. So you've got 2 functions, asymptotic, discrete asymptotic, one for functions, one for sequences. And of course, the question is, why do we need them? After all, we could just do this in some way or the other with series. Well, the point is that we really want to, we had these new functions called asymptotic integrate, asymptotic desolve value, etc., but you can't keep on doing that. So we need 1 or 2 master functions in which you can put what you like, and they'll go and do the right thing. So this asymptotic function, for example, can work with, let's say, Laplace transform. So here you have a function, a pretty messy function. It's 1 over e raised to t squared plus t raised to power 17. And of course, maybe you can compute the Laplace transform, who knows. It might take a very long time, but what do you do with it if you got the answer? So what do you do? Well, you inactivate, tell it don't do anything. Okay, stay where you are. Put it inside asymptotic like we've done over here. So that's asymptotic inactive Laplace transform. And lo and behold, you get back a nice approximation for the Laplace transform.
Question, why do you need inactive?
Right, so you don't have to, but if you didn't have it, it might take you 10 minutes for Laplace transform to tell you, I don't know. I mean, yeah, so here's the thing that if it evaluated right, then asymptotic knows what to do. If it didn't evaluate, it's the same philosophy as n. If you do n of integrate, if integrate worked, you're fine. If not, you can just do inactive. With a hold, we've kind of given up on hold because it's kind of programming construct. Inactive is much more a calculus kind of thing. You can do d of inactive, etc. The inactive is a mathematical operator in the real sense. So we kind of give up. Hold was what we did early on, but inactive is the way to go now. Okay, and that's a very nice approximation. But of course, you might say, I have a generating function for a sequence. What's the asymptotic for the sequence? Give it discrete asymptotic, it'll do it for you. I want to know the complexity of Karasuba multiplication, we'll do it for you. So that's a large program we have got called the asymptotic computation program, and I'll give you a brief idea about that tomorrow afternoon at 4 p.m. So that's one of the talks for our team. Okay, so now on to another theme, and that's special functions and mathematical functions. So we got these new functions called Heun functions. And what the Heun functions are, well, we have 10 of them, and the question is why, I'll tell you in a minute. But these Heun functions are great. So you learn about sine, cosine, exponential in high school, maybe. Then you learn about Airy Bessel if you're lucky. And if you're really unlucky, you need to study about hypergeometrics. And most of us stop over there, right? For Heun, hypergeometrics are a special case. So they encode sine, cosine, exponential, etc., hypergeometrics. They encode spheroidal functions, Lamé functions. I think the elliptics just about don't make it over there. But basically, this one set superfunction, Heun, will swallow up all the other functions into one gobble.
The question, a year or 2 years ago, you introduced to Mathematica another class of similar functions, Mir-G.
Mir-G is, okay, right. So Mir-G is a generalization of hypergeometric. And Mir-G will more or less be a special case over here. So this goes beyond Mir-G, far beyond that. Well, Mir-G is a bit different because it might have higher differential equations. So they kind of go in different directions. But Mir-G has been around for 30 years. And we have the world's expert, Oleg Marichev, over here. So Mir-G is one direction, and Heun is a slightly different direction. But Heun is what people need when they study quantum computation nowadays, when they do black hole theory, etc. So this is the rage in research in that area. And the question is, why is it different from hypergeometric? Well, hypergeometrics by definition have got 3 regular singular points, 0, 1, and infinity. The Heun function has got a 4th one at A. What's A? Well, the A you can see over here is a pretty arbitrary thing, and it can be almost anything you like. So that A can wander all over the complex plane and make things very difficult for us. So Heun functions are really the major advance for version 12.1. There are 10 of them because you need 5 Heun functions to account for all the confluence of singularities. Then to do calculus, you need a derivative, so you need 10 functions. But once you go to 10, you're all set, if you understand Heun functions. Okay, right. Okay, so, but the point is that we really have 250 special functions since version 1. So what we thought is that the real value for us is to keep up the documentation of these functions to a really high level. So for version 12, we added 4,000 new scope examples to 250 function pages. The person who worked on this has put in a lot of work, Anush. And version 12.1, we said, okay, let's go back now and add basic examples. So now version 12.1 has got new basic examples for all these functions. So for example, if you go to the page for sine in version 12.1, then if I scroll down a little bit, you'll see that we actually have a nice plot, a nice complex plot from version 12 for every function. So 250 new function pages, brand new from the point of basic examples. But that's a lot of work, about another couple of thousand examples over here. So, so on the one hand, we've got the Heun functions at the very upper end, and the low end, we've got a lot of documentation improvements. So that's a lot of things to talk about. And there's a nice talk which Tigran has prepared, which is at 12:30 today in the same room. So Tigran is 25, I may say. He has a double PhD. He got a double PhD while doing his work on Heun functions. He has 12 publications. One of the rare people who actually followed his father's footsteps. So his father's an expert on Heun functions. He's one of the world's experts on special functions. I invite you to attend his talk at 12:30. It's his first talk over here. Please encourage him. Okay, so now going on to differential equations. So in version, I've always had this feeling that, we are not good enough on first order ODEs. So for version 12.2, we did a survey of CUM-K and found we are not so bad after all, but we filled in all those gaps. But the real value came from using these so-called inactive integrals. So, people report to us that they got this DSOL example, which might take 1 hour to come back or not come back at all. What was happening was that we found one solution, then the other one was an integral, a difficult integral. We spent all our time, didn't know what to do. So this example at various times taken between 10 minutes and 1 hour. Now it takes 0.11 seconds. So just using inactive integrals made life much easier for us.
You increase the magnification?
A little bit, maybe. I could, okay. It might work. Let me see if that could do that, okay? Let me see if that might work. Okay. A little bit better? Sure, of course. No problem. Okay, so version 12.1, we have Heun functions. We need more linear differential equations. So version 12.1, we are filling up the linear differential equation gaps. Version 12.2 will be nonlinear and then system of ODEs. But I'm hoping the version 13 cycle, we'll be on top of the world in differential equations by our own reckoning. So that's the theme for ordinary differential equations. Try and cope up on benchmarks. Another very popular theme, I'm surprised how popular it is partial differential equations. So we have some nice support now for further heat equation, etc. We did some work for 10.3, 10.4, then we had done more on version 12.1. So that's a symbolic solution for the heat equation, the radial heat equation. It's a beautiful plot over here. And having done this, we decided to benchmark. So we have a benchmarking program where we essentially have one computer which just chugs away and does millions of test examples all the time. And every week you get a new report. So here's one of them, which compares us in various versions. So just a minute. Okay. So let me open the report up. It's a PD solve DSolve benchmark. It has got 1461 problems, and 11.3 we could do 54%, 12.0 66%, 12.1 71%. Maple is now at 60% below us with this improvement when it ships. SimPy is at 11%. I think Sage has got no support for PDs. So in this area, we should be pretty much at the top in 12.1. And how do we judge ourselves? So we have a way of judging the time we take to solve problems. We got interactive, well, we got instant time, quick, real time, a bit slow, responsive time, even slower, interactive time, background time, the kind of job you'd not let run while you're working on the computer, and then finally coffee time. So, okay, so we try and keep the coffee time down, but the computer doesn't need coffee. Yeah, huh?
Is it reasonable to get that goal eventually to 100%?
The answer is that we have a notebook with the 400 problems which you cannot do. I suspect that maybe 125 can be done. The others don't have proper solutions, or they might have a particular solution, and the developer keeps on telling me that no, we should return it with a message. I mean, I'm really worried about breaking our design, but yes, we have the notebook with us and we'll work on that. So that's Roger's point as well, that we should be at 100% or know why we are not 100%. But this over years, I would say all the examples which can be done reasonably with what we have right now. Okay, so another very nice program that we've got right now is function properties. So, you often want to know, is this function continuous? What are singularities? Is it injective? Is it bijective? Is it surjective? So we have a vast program, very big program. It's not quite ready. It's for version 12.2. Adam Stresbonsky is working on it. But for example, if you want to know, is this function of a max of log of abs x plus 1, whatever, continuous, it'll say, yes, it's true. it'll go back and you can see that that's correct from the graph. But the difficulty we have had is we've got these functions called q. So we've got prime q. And if you ask prime q, what's prime q of x, it'll say false. And that's not correct, right? Because you don't know what x is. So continuous function c is a bit cleverer. So c over there means condition. So it might give you back a nice condition. In this case, if you got this function over here, clearly that's going to be continuous if a is equal to 1. And this over here is a nice new typesetting for the conditional expression due to Itai in version 12.1. So you get back either true or false or a condition, or it might be very honest and say, I don't know, which is fine, better than having a false which is not a false. Okay, so there's a nice talk by this. This is very deep, difficult work. Adam works on it literally 8 hours a day, and he'll speak about today at 11:30 right over here. Okay, so now on to the next theme over here, which is perhaps very important for many people in this room as well, math education. So we have tried our best in version 12 to try and make the system more usable for high schoolers, college level, everyone. This has been a really serious attempt. And for example, you got this thing called add sides, which you can just add the same number variable to both the sides. I've taught middle school algebra for many years, literally in a classroom, and I know how difficult it is to teach algebra the first time. But we have this nice function, add sides, multiply sides, etc., which you can use to motivate students to do the right thing when you're in the classroom. And on the other side, I spoke about special function documentation. We have completely refreshed pages for D, limit, integrate. So we did D in 11.1, limit in 11.2. 11.3 took a break for asymptotics. 12.2 we did integrate. But these pages now have as many examples that you might want to know for a college calculus student or someone. And we also have these new interface developments, so you can figure out whether the multiplication sign not implicit in some calculation. It's all getting really very kind of powerful on the education side, but that deserves another talk, and in fact that talk will be given by Itai today at 11 o'clock. So I think that we really want to keep going on the education side and make things much better. One last thing that personally I worked on this Introduction to Calculus MOOC a couple of years ago, started work. We shipped last year, and I always wondered, is it really worth my time? And why bother, kind of, you know? Well, it shipped, and then a few months later, someone from Nigeria, lives in a village near Abuja, had to travel 2 hours a day to get to school, would scribble Mathematica in his notebooks, go to school, try it on a computer, didn't have money for the bus. He sent me his certificate, said, I've done it. It seems to me that this is the best way for us to reach the world, do online courses. So I've put in a lot of effort in the last few months to prepare this new course, Introduction to Algebra, which basically focuses on matrices, but also does vector spaces. So you see where Arthur Cayley, Sylvester, Kramer, Piano, Gauss, they are all there in the course. It's a very nice course, I think, 25 lessons, and you go from 2x2 equations to singular value decomposition in 25 lessons. And we want to have some more courses, but I want to wait for you to tell us what you want in terms of future courses. So if you have some thoughts, do let me know. And I'm almost done. Well, I'm done really. So just want to summarize and say that we have a very active development program. We're doing asymptotics, special functions, function properties, differential equations. But when Roger set up the team a couple of years ago, we were never a team really. We just loved to do what it is. We didn't need a team for that. Okay. He said, let's talk about development. Let's talk about documentation. Let's benchmark and figure out how good we are. If you're not so good, be humble about it. If you're good, be proud of it. And finally, go out, do some outreach, reach the world. So that's the kind of thing we're trying to do. We're doing development, documentation, benchmarking, outreach, and I think it's worked out so well so far that we are encouraged to go on. So thank you very much. I'll stop over here.